Okay, so give this your best shot. We'll give you about 5 minutes. It gives you KC in the bottom right-hand corner. You're calculating Q and comparing it. All right, I'm going to pause this. So it gives you these three values, and it gives you sorry, just get annoyed by my child sometimes. SO2 Cl2 over SO2 Cl2. We okay with that? Okay. Q and K are the same expression, remember? So here we go. Please stop talking. 0.035 is SO2. It tells me that right there. This is in a dumb order, but whatever. The bottom then is 0.5. And then Cl2 is 0.08. So you plug those numbers in, and I have no idea what number you get. 0.0056. Okay, I got more than one yes. All right, and is that K or is that Q? Q. So remember, I'm going to put K and Q in alphabetical order. You all right with that? Q is 0.0056. K is given to me up here. It is 0.078. All right, which one would the alligator eat? It would eat K. K is greater than Q, correct? Which means, turn this into an arrow. Which direction is it going to move? No. Shifts to the right, which is where the products are. Not that bad, was it?
No.
What? That's all.
Yeah, I was thinking.
That's all. No. It gives you current concentrations. Like at this specific time, we have these concentrations. Then it gives you K, which would be those things at equilibrium, and it wants to know which direction it has to go. Yes. It would be different, but we would never have to do that math. She said, is it different for a temperature? The answer is yes. Every one of these problems is temperature dependent, but we never have to consider the temperature. It'll just be written as part of the problem. So you don't have to stress about that. Okay, let's see what I got here. Oh, I don't. Could you do that problem now?
Yeah.
All right. How do you know? How do you know it's a Q and not a K problem? How can you read it and know? All right. It gives you K. And it also gives you the current concentrations. Which direction will the reaction proceed in order? So we would say towards products, or you could say the forward reaction. That
products, it's always products over reactants.
Okay, are we all right with that? Because we're going to move on to something that's similar but a little bit different.
So we choose which ones in order to decide which one's reactant that we can
I got those from here. These are my products. Yeah, it was written poorly. I'll give you that. Those are my products. This was my reactant. Okay, good. Yes.
So when it's written with like the arrows pointing both directions, you just say the way that they have it written.
From left to right is the forward. Right to left will be the reverse. And you'll see a lot of the double arrows. It means it's a reversible reaction. It can go both directions. Okay, questions? We're going to pause on the math for a while. You all right, Tim? Okay. And we're going to talk about Le Chatelier's principle, which you've never heard of before, right? Le Chatelier's. It was in the GIM kit. All right. All right. I have, this is my Le Chatelier's principle demonstrator. What are the odds this tips over? Pretty high. Okay, everybody look right here. This is my Le Chatelier's principle demonstrator. I'm going to put water in these bottles. This side's going to represent the reactants, and that's going to represent the products. Fair enough? Okay, good. Now I need some food coloring, which is in the back. If only I had something really brightly colored to put in there. But I can't, Delaney, those are toxic. All right. What? Yeah. Oh, you can. So I'm going to put some food coloring in here, and then I'm going to add water. Or
You're not my mother.
I'm going to add reactants. At some point in time, the concentration of reactants is high enough that a reaction starts to happen. Can you predict when that would be? Oh, probably when I get to the tube. You guys are smart. All right, so I get to a certain point where my reactants start to have enough concentration that they run into each other enough that a reaction starts to happen. Fair enough? All right, now let me fill it up till I reach what we call equilibrium. Tell your partner what equilibrium will be in this demonstration. Just gonna add a tiny bit more. Okay, so right now, like, I don't know, 46, I've taught for 20 years. I'm not going to talk over people. That's just a waste of my time. So you waste your time instead. Okay, this is at equilibrium. I have a question for you. Are there equal amounts of water on both sides of this thing? No, this tube represents the arrow. You okay with that? Water could go that way and it could go that way. Can we all accept that? Okay, good. This is a reversible reaction that is at equilibrium because the rate that the water is going that way is equal to the rate the water is going that way. Easy, 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 right? Okay, Le Chatelier's principle says if I stress a system at equilibrium, it will fight or oppose the stress I put onto it. So what it means by that is if it is at equilibrium and then I disturb it, an example of disturbing or stress is that I add more of one thing or the other. So I came along, it was at equilibrium, I disturbed it. What will the system do to fight that? It'll go away from where I just added, right? So if it's at equilibrium and I add reactants, the reaction will flow towards the products. It will oppose every single thing I ever do to it. That's Le Chatelier's principle. Yep, it always wants to reestablish an equilibrium by doing the opposite of the stress you put onto it. Okay, so my example here is I increase the concentration of the reactants. Now we should know by now, the more reactants, the faster the reaction rate, right? Now the forward rate. So I made it out of balance. The reaction sped up until the products were being formed, right? You get to a certain point where now the concentration has gone down, the concentration has come up, and it reestablishes a new position for equilibrium. You okay with that? That's all that Le Chatelier's principle says, that a system will fight or oppose any stress applied to it. Now, I have a simple sentence, if you remember, from regular chemistry, and it is add, away, take, I stay. Add, away means if you add to one side, the system shifts away from that side. So if I add reactants, what direction does the water flow? It flows away or towards the products. You okay with that idea? If you add, you always go away from the side you added, because it will always, always oppose the change you make to it. Okay, so the second half is add, away. The other half is take, I stay. So I poured a little too much out. Oh, whatever. Okay, so I'm going to simulate removing products. And for some reason, this really gets kids. If I remove products, the system wants to fight what I just did. So I'm going to blow in here. I can't pour one out. So I'm going to blow into this, and then I'm going to cap it. Okay, so pretend I emptied some of these out. It's weird, but by removing products, what is the system going to do? It's going to make more products. Okay, so literally taking it away causes more of them to be formed. So like Seth, I know he works at Peach City. If people order more hamburgers, you have to cook more hamburgers, right? If they don't, you don't, right? So just think of this as a product that sells. The more you sell, the more you have to make of it. So if I remove from one side, the system comes towards the same side I just removed from, because it's always wanting to establish, what do we call this right here? Equilibrium. Now, tell your partner why one of these is on a block. Okay, good. I heard it in the front row. It's to show that equilibrium does not mean equal amounts of water. It means the amount of water is not changing on either side. Are we okay with that? Okay, this is the basic introduction to Le Chatelier's principle. If you stress the system, it will oppose every single stress you apply to it. Now, there's more notes to go with this, but as we go through this, think about this simple demonstration. All right, so here we go. If a system at equilibrium is disturbed by a change in temperature, pressure, or the concentration of the components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. I wouldn't write that down. A system that is stressed relieves the stress. It fights everything you do to it. It's like a teenager. Okay, ooh, clean video search. What do we think this is? That's a dot.
It seems safe.
Seems like nothing's happening over there. It's blocked. That'd be so funny. Well, that's convenient. And I don't even remember what this video is, but it tells me that clean video search is no longer a thing. I appreciate that.
Well, if you look at you with the back half of it, you might be able to
Right here.
Or
Who cares?
I don't know how to do it.
I don't.
I think we should leave the link in just so like next year you can choose to.
No, this is what I'm gonna do. I'm gonna nuke it. Boom. It was great.
Can we have a few more for that video now?
No, you can have one after school. All right. So think about this once again. if I removed water, it wants to fight that by making more water. If I add more water, it's going to fight that by going back to the hydrogen and oxygen, so to say. Okay, it will always oppose the change you're trying to do. I'm telling you, it's just teenagers. Like if I want my kids to do something, I can't tell them that I think it's a good idea. I have to tell them they can't do it. All right, now we need to talk about all three types. There is changing concentration, changing temperature, and changing pressure. Those are the three conditions that will affect the equilibrium position of a reaction. So I would not, once again, write every word down here, but changing the concentration of a chemical will shift the equilibrium to the side that would reduce the change in concentration. The chemical system will attempt to partially oppose the change affected to the original state of equilibrium. In turn, the rate of reaction extent and yield of products will be altered corresponding to the impact on the system. Okay, so that's a lot of words. Tell me what happens in the summer when you're trying to make a campfire and you blow on it. It gets bigger because you are giving it more reactants. So it opposes your addition by saying, fine, I'm going to make more products then. Well, you want the products, right? You want the heat. You want that thing to break the wood down and give you the heat. So by adding one of the reactants, you made it make more products. Fair enough. Okay, it will oppose everything you want. How do you put a fire out? You take away the air, and we usually do that in our world by water. You smother it with water. Did you know water is a product of a combustion reaction? You flood it with its own product. There's too much of it, so it tries to go back to reactants, and it can't really do that as fast as you're pouring water on, so it's out. Okay, like all these things sort of make sense. You're upset?
Wait, does that mean you
Oh.
can unburn?
You can sort of unburn. They're not, burning something is not really a reversible reaction. So it's like, we would never write the equilibrium for it, but just the example of using the reactants or products to get it to change, it works fine. But yeah, you can unburn. It just takes a ton of energy and organization to do it. The sun basically is unburning every day that it's growing a plant. So I don't know. It is weird. When you burn a piece of wood, you're just getting the energy out of the 30 years to grow that tree from the sun in like 20 minutes. So all that sunlight energy went in and you're getting it out in a really compact, fast way. So, okay, are we all right that it will oppose? All right, I would memorize the phrase, add, away, take, I stay. And what, I'll just write it out real quick. So like A plus B goes to AB. If I add some A, the system will move away from that side. Fair enough? If I add, I always move away or to the other side. So if I add reactants, I make more products. If I remove or take away AB, like together, then A and B want to combine to make more AB. There's more space to put AB. So if I take away, I stay on the same side. If I remove a product, I will make more product. Go ahead.
This, you add like more of one, but there's less of the other. Will it change very much? If there's not enough?
Yeah, if you run out, if one of these is a limiting reactant, then you'll still establish an equilibrium. It would just be like having hardly any water in one and a lot on the other, if the straw was like way low or something. Yes.
So is this saying that if you like change the concentration of the reactant side, it would remove reactant, it would remove concentration of the product side?
Did you say remove and remove?
Yes.
No. I will tell you these two things right here. If you change one, the other one will do the opposite. And then the sides will always be opposite of each other. So it can't, you said remove product and remove reactant. You can't have the same on both. Now, these two can be the same if you change A, B. Go ahead.
So the only thing that matters is the amount of the product relative to the amount of the reactant or vice versa.
Yep.
Alright.
We're like in this example of the bottles, when we say equilibrium and like reestablishing it or whatever. Oh boy, what did I do here? Okay, whatever. Screw this.
Oh, let's try and make it sound good. Fancy.
I feel much better about this one. Okay, this is the block, right? When we talk about the equilibrium position, we really mean the math. And we would compare the height of the products. Let's pretend that's, well, it'd be from here. Sorry, it'd be from here, not there. We'd say, this is a 9 and this is like an 11. Be okay with that? So we would just say we have 9 11s. That would be my equilibrium position. That's all we're changing. If I add products, I'm going to start shifting over here. And the products, they go up a little bit to like 10, but these go up to like 12 or something like that. So now I have 5 6 instead of whatever. We're changing that number. The number will change, but it will still be at what we call equilibrium. Okay. Oh, that button. How about I just go like this? See ya. What the? Okay, Tom. Okay. Coming back. All right. So far, sort of all right. So talks about the Haber process. The transformation of nitrogen and hydrogen into ammonia is of tremendous significance to agriculture, where ammonia-based fertilizers are of utmost importance. If we don't have ammonia, we do not get as much yield out of the ground, and we're in a lot of trouble. This really is an important thing. In this reaction, you have N2 plus 3H2 goes to 2NH3. If I am a producer of ammonia, tell your partner how I can make this constantly make product. There's a couple ways to always get this to shift towards the product side. Okay. Tim said, take away ammonia. Absolutely. A chemical engineer is smart enough to know Le Chatelier's principle. And if they constantly want to have product as their yield, like what they're making is always product. Did I kick you? Oh, well, that's weird. I thought I touched something. Then the best way to do that is to make sure that as soon as this is made, get rid of it. So think about it like a bike maker. If they want to constantly be making bikes, they dang well better be selling them. And if they don't, they're eventually going to fill up the factory and there's nowhere for them to go. The whole system will shut down, right? So in order to optimize the yield, we remove the product as fast as we can. Then obviously also we need to what? We need to constantly be adding reactants to this. Ammonia is actually really hard to make. It takes a ton of energy. It's one of the most energy intensive things, that and aluminum, 2 things we use a ton of, all right? But if we optimize the conditions, we can get ammonia to happen pretty naturally. Okay, sort of all right with that? So that just says add away, take, I stay again. Here's a good picture of what we're talking about here. So it is at equilibrium right here. The lines are flat. Okay, whenever you see one of these graphs, the vertical one is like when we, the human being, makes a change to the system. It's not the system doing anything. We opened up the container and we poured more H2 in. You all right with that? Like that's what the vertical line is. And we don't explain the vertical line. We explain what happens after, how this went down and this went up. Ooh, look at that trace. All right. So it should make sense. We saw this as let's see how much we got in here. The vertical line will be represented by me when I cap this. So I won't let the reaction happen yet. It would be this change. That's the one that's straight vertical. And then it doesn't take any rocket science. Like I could bring my 7-year-old, 8, she's 9. She's 9. I could bring my 9-year-old and my Carly could say, yeah, the water's going to go that way, right? She what? Yeah, I don't really understand what happened that night. My bad. Okay, so everyone look, the vertical was when it went up. It's obvious that this is going to do what? Go down. So that's the green sloping down, and it should be obvious that this side must go up, and that's the red slope. It's all right here. Don't overthink these. They are actually really simple. Why did I bring my slate over? Okay, are we all right with identifying what they look like on a graph? Yes, absolutely. All this water gets you. All right. This apparatus helps push the equilibrium to the right by removing the ammonia from the system as a liquid. You don't have to draw this out, but it's pretty interesting, pretty fascinating. As soon as it is produced, they try and get it out. All right. It's any chemical engineer is going to try and design a system where the product is removed as fast as possible. So you can get as much as you want out of the reactants, because you're going to pay money for N2 and H2. Like these are your input costs, and you're going to make money off of your NH3. So if you create an environment where every dollar you spend is turned into every dollar you can make, then that's good. Like that's the whole point. You don't hire a chemical engineer to have excess reactant. No one wants that in their lives. All right, the effective change in temperature. Now this is a lot of words, but just stick with me. The effective change in the temperature in the equilibrium can be made clear by A, incorporating heat as either a product or a reactant. All right, so we're going to write the reaction and we're going to put heat either on the left, which means it's endothermic, or the right, which means it's exothermic. All right, when the reaction is exothermic, what I just said here, delta H is negative. That means energy is given out. Heat is included as a product. And when the reaction is endothermic, H is positive. That takes in energy. It is a reactant. Hence, whether increasing or decreasing the temperature would favor the forward or reverse can be determined by applying the same principle as with concentration changes, which means add away, take, I stay. So follow the logic here. We have ammonia again. It says that delta H is a negative, which means that this is an exothermic process. Exothermic means heat exits the system, or it means that it's a product. Thank you, Keely. They want you for your appointment right now. I'll bring it to you. Okay, so I would write my reaction out and I would have heat as a product. I literally put a plus sign and then put heat. Are we okay with that? Okay, and then we do it the same exact way. If this is producing heat and I add heat, it will oppose that by going away from the heat term. So just kind of think about this. This reaction is producing heat. Does it want to be in a hot environment then? No, you just ran a marathon, the St. George Marathon. You want to go get hot chocolate? Not a chance in the world, right? Chemistry is the same. If it is exothermic, it wants to happen in the coldest environment possible. If it's endothermic, it wants to happen in the hottest environment possible. Like if we want to melt the most ice possible, that's an endothermic process. I'm going to put it in the hottest water possible, right? Okay, now the term add away, take, I stay works exactly the same. If I add heat, I move away from the heat term. If I cool the system, I circle the heat term. I'm removing, so I go towards the heat term. If you cool it, it will go to the side that produces heat. It always wants the opposite of what you do. You heat it, it wants the cold side. You make it cold, it wants the hot side. So if this is true, and it is, this is a real measurement. If this is true, tell your partner, besides what we already said, how we could make the most yield of ammonia. What would you do? We want the most NH3 produced. At what temperature would you want this reaction to happen? Not going super well. Oh, you want to heat the reactants? You can't, you have to heat the whole thing. You can't just heat the reactants. So this is all, that's tricky. I guess I should say, this is like happening in a flask.
I really like that class.
There's things in here. I can't have them really separate because they have to combine to react, right? So heating reactants or heating products isn't an option. You can either heat the whole system or cool the whole system. So looking here at this answer, the way to get the highest percent yield is to cool this system as cold as possible. Yeah, they go to liquids and that's okay.
Wait, does the reaction still happen?
But does the reaction still happen? Here's the deal. Good questions. This reaction is actually done at a really high temperature. Well, what else have we learned? The what? No. It starts with an R, ends with 8. The rate.
Oh, because it's so fast?
So it's not so fast. If you make it really cold, you get a higher percent yield, but it takes way longer for it to happen. So they want it to happen fast. So they sacrifice yield for time or speed. That is a question on the next test. This exact thing is discussed on the test. And it says what conditions are the best to produce the most or the highest percent yield of NH3 or something like that. And then after that, though, it says, but the reaction is actually carried out at high temperatures. Explain why. And I've given you the answer and I'll give you it again. Because they don't want to wait 10 years for it to happen. In 10 years, all of it's going to be NH3, and that's great. But that's 10 years from now. If they do it really high, they get some product, but they get it immediately. So they sacrifice percent yield for speed. You would want it so far where you remove NH3 and at the lowest temperature possible. Just all you have to say is at a low temperature. You don't have to get specific. We all right with that? Okay. It's a good thinking question. Okay, there's a third one we got to talk about. That's pressure. I don't know how many words I have for pressure here. Oh, look at that. I've had this exact same system or discussion. Which flask was better?
I think that flask is the best one.
Yeah, I spent a lot of time on this one. Okay, changes in, ooh, what do we call this kind of flask? It's a Florence flask. This sounds perverted, but because Florence has a round bottom. Okay. Yes, they're not graduated. Well, there's Erlenmeyer flasks, which look like that. Ooh.
Oh, you were really close.
This was a good start.
Yeah, you got like halfway through.
It's pretty much,
Only half of the mirror.
it's like every heart I make. Only half of it, yeah. Anyway, so you had to memorize in college the types of flasks. And there was Erlenmeyer, there is another one, I can't remember. Then there's Florence Flask, and I remember Florence has a round bottom. Okay, moving on. Okay, here we go.
Certain liquids out of.
Pressure. It only matters if you have unequal number of moles of gas, products, and reactants. Because pressure doesn't affect liquids or solids, right? So it has to be gases, and they have to be unequal. A lot. Most everything. Now, yeah, when I say unequal moles, I don't mean you got to do any math besides adding their coefficients. Like we're not going grams to moles or anything like that. No picket fence. You just look, and Timmy already said it, you had a 3. If there's not a number, it's a 1, and then a 2. So what you would do for pressure here is you would say, all right, I have 4 moles, 3 plus 1, of reactant, and I have 2 of product. I don't know why I did what I'm doing, but whatever. You with me? I don't even understand. But okay, so you tell me which side has more moles. The reactants. Okay, my friends, reactants. Sorry, let me start that over. Moles take up space. They take up space. You with me? In fact, and don't worry about the numbers here, this side would like to have 88 liters of space to hang out in. This side only needs 44 liters. And that's just by going from moles at STP to volume. Just trust me for a minute. We use Pivner. All right, so which one needs more space? The reactants. So these, if they could, they'd fill up like a big box, and this one would fill up a small box. You kind of with me? Okay, so kind of think about moles need space. But what does pressure do to space? It makes it smaller, right? So if I squeeze my container down, which side is it going to want to hang out in? The smaller side, right? So an increase in pressure favors the one with less moles. A decrease in pressure gives it more space, and the system shifts to the side with more. One second, what? The side with fewer moles. Okay, it'll probably say it on this slide right here. Or it doesn't. Good job, Tom. You're a hero. I know. We don't all wear capes. All right, so here we are. We have this reaction happening. We are chemical engineers and ignoring everything else we've talked about. But now, based on pressure, how do I get the greatest yield? High or low pressure? High pressure. High pressure favors the side with the least number of moles. So the more I squeeze it, the more NH3 I produce. So to get the highest percent yield, we need to remove NH3, right? This is concentration, not pressure. We need to have the system at what temperature? A low temperature. Now, remember, really rate-wise, it's going to be high, but for percent yield, the lowest temperature possible. And then we want it under what pressure? High pressure. And this is actually done at an extremely high pressure. It's like 800 ATM or something like that. It's ridiculously high. That's also, what's that? They put it in a really strong steel container. These things right here, this picture, very, very tightly sealed. Lots. No, that's a real picture of a Haber converter. It's technically Haber, if anyone cares, but no one's judging me. Yeah. What? Nope. Okay. So that is with Chatelier's principle. Here we go. This is a typical question that you'll see on the exam. Or let me restate this. This is a question you'll see on the exam, which will happen this week. Perfect. I'm going to be gone 2 days. What a beautiful time to give a test. Thursday and Friday. I'll be chilling with Timmy. Oh, to partying with the distance runners down in St. George, St. Jeezy. So, which means you'll test one of those 2 days. What? You, that's a tradition. Anytime Brooklyn's gone, we're going to test. Okay, focus on that, not me. Yeah, I can have you do it on the bus. As long as we turn all Wi-Fi off.
We'll be in the middle of nowhere.
Yeah, that's true.
It'll be the best thing to do.
It's going to be not very warm, unfortunately. Okay, do you have an answer? Whew.
Oh, wait. That's the one, yeah. No? Pressure wouldn't matter. It's like equal. No.
How do they get on the ground? My son is a hero. He just won Best Actor for the USU Chinese Film Festival. Alan Davidson. I don't even remember him acting. He is. He and his 4 friends climbed out of a basement window I didn't even know you could get a human out of. It was super impressive. It was like the house. Can I say that?
Yeah. Wait, are you recording?
All right. Yeah, someday you'll understand. Yep. What? No, it was part of their video of escaping. I have no idea where it is. It's super dumb. It's in Chinese. Okay. Shh. Be ready? Davis is ready.
He's also awake.
Okay. The first thing you should do, it says it's exothermic. So don't leave that in your head. Put it down here. Exothermic means heat is a product. Okay, now let's go to town. It does say they're gases, so I have a 3 and I have a 2. Are we okay with that? You should do that as well. All right, I want that a change will result in an increase in the number of moles of SO3. So I am looking for something that makes the system go this direction, correct? Okay, will increasing the pressure make it go that direction? Yes, that was a letdown. Okay, let's check the other ones. Let's see F, all the above. We better check them, right?
Yeah.
So here we go. Increase of pressure, that was correct. Decreasing pressure, well, that's the opposite. So we know that one's wrong, right?
Now we can make sure that's not have to be done.
Yep. Both A and C. A, B, C, D, F, G. Okay. Increasing the temperature, I would circle the heat term. If I increase, I go away, which is not what I want. Removing oxygen, if this side goes down, it shifts towards the side I removed from. So that's not what I want to happen. Increasing the volume is just the same as decreasing the pressure, right? Okay, you got this one. Not too bad. Okay, same exact thing. This time it's giving you delta H is negative 99. Negative means it's exothermic.
Yes.
Okay, try it. Hopefully it's not A this time. It could be. I haven't looked.
What's the part you crossed out?
The delta. I just said plus heat instead,
Good though.
but it was kind of ugly.
Yeah, but the partial pressure, like, is what part of it that has the three, that will change.
All right, what's the answer? It's A again. How lame is that? What a letdown. It is A. So heat, if we increase it, we would go away, which means this stuff goes down and both of these would go up. You okay with that? And that's what it's asking. It's asking what's making this go down. Okay, here we go. You just saw the answer. It's not A. Okay, give it a shot since maybe you didn't see it. Am I in your way? I am in your way. Sorry. It's what I'm best at.
I'd rather hear it.
Oh, aren't you sweet? I'm going to go all the way over here. Oh, you know what? It's lunchtime. What does that S matter? Yeah, definitely. It's not really a huge deal. In this problem, it won't really matter, but it can.
explain the effect.
Here we go, my friends. So we have this equilibrium. At equilibrium, some solid remains in the container, which is good. Predict and explain each of the following. So this isn't A, B, C, and D, I guess, anyway, is it?
Yeah,
Okay,
it's like explain all of them.
I was
Okay.
extremely busy thinking which one.
well, when we came here, this was circled, but it must have just been talking about that. So here we go. The effect of NH, so we want to know what happens to this when more of this is added. So what happens to the NH3 when I add more of this? It goes up. Are you okay with that? Okay. So I'm going to get rid of that. It's still asking you about NH3, which is green here, when H2S is introduced. When we add more of this, what happens to it? It won't matter.
Irrelevant.
The reason why it won't matter, we should know H2S is a very, very low boiling point gas. You may not know that, but it will vaporize pretty much immediately. So if I increase this, what happens over here? This one comes down. Are you okay with that? All right. Now, we want to know the effect of NH4HS. When the volume of the container is decreased. All right, how many moles of gas are there over here? 0.
It was solid.
It won't matter because you would have put a 1 anyway. This is a 2, right? Right, so it would have been the same even though you made that mistake. But be careful when it's a solid. Okay, if volume is decreased, that really means the pressure is going up. If the pressure increase, I favor which side? The smaller value, which is the one I've highlighted. So this one, the solid would increase. Kind of makes sense. You have gases that you compress, they should probably want to get out of being a gas. You're forcing them together. Okay, now it's still NH4HS. I don't know the name of it. What does it say? Does it say? Nope. It'd be ammonium hydrogen sulfide or something like that. It's a weird one. If the temperature is increased, so this is a positive. So where's the heat term? It's on the left. Okay, so if I increase, I go away from the heat term, which means this would go down. Oh, speaking of going down, that's the end of class.